Today we're going to talk about asynchrony in Sharp and what pitfalls and traps you should be aware of. For example, you might have heard that if you misuse tasks and asynchronous expressions, you could land yourself in an unpleasant situation, most commonly deadlocks. And that's typical of UI heavy code. And this is one of the most simplest examples you can come up with. Let's assume we have form and we want to update one UI element. So as you can see in this case, I have an event and its handler, which is declared as an asynchronous method in a class definition of the same form. It's a synchronous void because that's the only way you can, unfortunately, bind this handler event and then catch event and react to whatever you're supposed to react. In this case, it's a click event. So let's dive into it. So we first create a task by calling this writeTextAsync method. As you can see, it takes text as an input and returns a task. And it does so asynchronously. It has an await expression here. Will simulate an asynchronous operation that it waits for asynchronously. It's just a stupid half-second delay. And afterwards, after I've waited, actually write whatever we want to write. In this case, we will just modify a reach text box property, the text property, and simply, well, append to it as if this were a console, kind of a, UI element. Let's look at it in action. And obviously this should work pretty perfectly, which it does. So as you can see, I can click it tons of times. It has a minor delay. It writes the text before deadlock, then await the task that we've created. And after I've finished waiting for that task, we know the task is done, we write after deadlock. This is pretty fine, but the troubles start when you actually disregard a few things. One of them is the so-called synchronization context, which in case of UI calls is pretty strict. Not allowed to update UI elements from anything else but the same thread. Usually that's the UI thread the application creates for you under the hood, and you're supposed to perform any actions on the UI elements from the same thread. Nothing else is allowed. Good. So this is called a synchronization context, meaning the rules that come with this mode of execution functionality, what you normally call the context. What we do here on so-called UI thread, we wait asynchronously. Then, if you don't believe me, what this allows underlying execution flow to achieve is actually all this whole thing execute the body of this method on the same UI thread. Thus, we are restating the constraint that any element should be updated from the UI thread. Pretty fine. But if you think about it, event handler, this method is already called the UI thread. So at this point, find ourselves on the UI thread, and then we launch a task asynchronously, and the task should be executed on the same UI thread. So how can this be? Because that could give you the impression that overall you are blocking yourself. You are here, need to execute something on the same thread, and yeah, um, your thread is already waiting for that something to be executed. It's like a vicious circle. Well, that's not really the case, and what we also want to explore today in a lengthy presentation, unfortunately. Well, that's not the case because the compiler does something quite involved, and it's amounting to more or less chopping up this whole function in sub-functions and orchestrating slash scheduling them. And well, without diving into details, lengthy intro, it does so by keeping a list of states and running a so-called state machine for you. And you don't see that, but the compiler just actually generates hard-coded implementations of state machine-like objects. Where does the context come into play? Well, we only have one thread from which we can update these things, and that's what we don't see explicitly. We inherit whenever we get called with the button one click method, we inherit the context of the caller. In this case, the context dictates that everything should run on the same UI thread. So you could say that, well, I'm just at this point creating a task, and if I were not to call this method like this, so create a task, and instead just call it synchronously, you would say, well, that's pretty simple because I'm on the UI thread. What I do there is and call this method, so just enlarge the call stack by 1, end up in a different function call, wait there, perhaps blockingly. Yeah, and then after we're done, we can write a text. Well, not actually what happens, but it's what most people that are not familiar with the async-await functionality and paradigm will actually hope will be happening, or that's their expectation there. And that's not precisely what's happening, and exactly why. If that were to happen, so if this thing would be called instantaneously as we enter the button one click method, then we should not see the before text be written after, actually before the deadlock sorry text. That's not what we saw. That we first have the before deadlock, then sandwiched between before and after we have the deadlock text token, and then the after deadlock token. It's like a small code block, if you will. So why is that? That's what we want to find out. To follow up on that point, let's assume not to wait for the task any longer, and we just call this function, or at least assume we can call it right here. So the expectation one who reads this might be, oh well, the function gets called, so the write text async call directly. Wait here. Notice the wait expression where on milliseconds, then we write the text to that text box. And then write before deadlock and after deadlock. So what we should see in the output is deadlock, before deadlock, and after deadlock. Let's click the button. Well, as you can see, surprisingly, the inner contents of the sandwich fell out. Have quite the opposite, before deadlock, after deadlock, and deadlock written. Well, why is that? Because in this case, decorating things with a sync keyword changes the behavior quite a lot. And what actually happens that we are merely launching a task. We're not waiting to finish. And because we have this delay here, we get right our before and after deadlock operations, perform them, and eventually after the 500 milliseconds elapse, able to continue, and I emphasize the word continue, write whatever we wanted to write, in this case deadlock, to the output text box. Let's make things a little bit more interesting. Let's assume we actually are not allowed to have an asynchronous event handler here. So in this case, the assumption is that things plot. Let's see what happens. Execute this of code. Well, click the button. It's that correct. The same thing happens. So the task will be executed at some point, meaning this delay is still applied, but because we're not actually blocking, so when calling this method, we're creating a task. That's it. Get to execute the rest of the operations embedded instantaneously without waiting. Task is just like a resource, a variable. In this case, a variable that we don't even store explicitly on the call stack of the function. So might as well say that we are leaking resource case. Because as you can see, execution is still scheduled and it will still happen at some point. Now, let's say I don't want things to happen like that. What can I do? I want the deadlock text to appear again inside the before and after sandwich. I could be tempted to put it here, plain and simply, but I'm not sure that this will help. And it's easy to actually convince ourselves by simply rerunning. Obviously, it will not help, but let's try it out anyway. Yes, same behavior as expected. So what can we do? We want this to behave a little bit synchronously, and we want to actually have the guarantee that the deadlock text has been written before we write the after deadlock text. Well, as I told you, this returns a task variable, task t, so we can write such code and create a variable assigned to it and to simply block on it. I mean, that's the right word, make it wait. One way would wait and wait method of task, and let's see what happens. Oh, we are here. Can simply press the button again, and what's the thing you expect to see? Let's see. Well, I think half a second has elapsed already, and I'm not seeing the deadlock text being neither the after deadlock. What could be going on? that's pretty much revealed in the full stack parallel stacks windows. And as you can see, we have on a call stack this very nice information waiting on a operation. And here we also see that something scheduled. So we got a promise that something will be delivered in future, which is another way of thinking about async-await combinations. I think in computer scientific terms, things are also called promises and futures. Well, so what happens in this case is that underneath wood you have the synchronization context obliging you to make sure that the scheduled task, this operation here, C was indeed scheduled status. And if I get the task T and I see its status, it tells me waiting for activation, much the same as waiting to execute, and the result is not yet computed. Well, that happens because the wait call you see here is blocking. So we have a resource that we simply block. We wait for that resource to be taken care of. But we can, because if we do this on the same thread that's supposed to actually perform the workload associated with that resource, we're creating effectively the very nice, as the name indicates, deadlock situation. And from here onwards, the battle is lost. So, what can we do to get out of it? There are several things we can do. Let's see how nice or actually bad of an option each of them might be. Well, the first nasty idea that comes to mind, at least for me, is to explore what the wait function itself accepts as in the sense that it's overloadable. The first overload I can see is that it accepts a number of milliseconds. It tells me that what it should do is wait for the task to complete execution within a specified number of milliseconds. It returns true if the task was completed successfully with a lot of time, false. And believe it or not, this will not create a deadlock. However, that's not same thing as saying this will execute correctly, or not in all cases, but nevertheless, let's give it a go and run it, convince ourselves of what's happening. I press the deadlock button, I see the for deadlock, and then, well, nothing happened. Let's wait for it. So 5,000 seconds, milliseconds elapsed. Then I see continuously after deadlock and the deadlock text. Well, this kind of sucks because, well, I am out of the deadlock now, but I haven't really achieved what I want to do. As order perspective, deadlock text is not sandwiched and after text. Of course, I can try and hammer it and play around with this wait time limit, and can even say 100. That works. Borderlines. Let's give it a go. No, that did not work. And let's make this 400. It's less than what supposed to be before. And as you might expect, I would expect it that shouldn't work because within the allotted time we can at least mathematically finish whatever we're supposed to be. Well, we haven't, but it still worked. Why did it work? Well, let's see. This function returns Boolean, tells me that the task actually finished while trying to wait on it, so I can do this, write text. So I'm writing it synchronously. I'll just write finish. Voila, that should and uh yeah, and playing around with it. Know what happened. So finished is false. Actually, at this point, I don't have a guarantee that when I'm writing the after deadlock, that my task that where I was supposed to be waiting for was, well, performed successfully. So what actually does happen? We haven't gotten rid of the deadlock, merely failing. So let's wait for 1 second. We are still in a, well, deadlock situation, but whatever we get here is all a false result, no matter how long we wait, even if whatever, 1 hour, then still see that the task has finished because it is still scheduled to run on the same thread where you wait. So you're blocking the thread, but in this case, not blocking it forever, you're just saying block it for maximum this many seconds. Of course, you should believe me, but let's look at it and see what happens. So, again, finished false after deadlock, of course, and then the deadlock gets written here. Now, I have east, I've exited this call stack, I've the UI thread, and the UI thread is finally able to take on this operation that was scheduled onto it. As long as at least the process is alive. It is because deadlock text written here. Pretty convenient and at the same time pretty dangerous stuff. So we haven't actually managed to solve the problem. What else could we do? Ask a chatbot in this case. I'm asking Copilot what to do. This is for instruction purposes, so educational purposes. I'm not saying ask chatbots what to do without thinking at least. But let's see what the chatbot suggests. Well, it actually tells you that calling an async method from a synchronous method can be tricky due of deadlocks, which we know, especially in environment synchronization contexts like a UI application. Well, are there? Here are some strategies to achieve this safely. First one, the chatbot suggests task run. So from my synchronous method, I can do this, call the task run, which should schedule the operation execute on a, well, it says a background thread, but I think more accurately this could be described as a thread from the thread pool. Well, nevertheless, let's try it. I will copy and paste and adapt. I did task run LLM suggested, and we have an asynchronous lambda expression, well, lambda awaitable await task by text async call. Then for this runnable task, runnable expression, we get its awaiter. Talk about task awaiter later, and try to do all will achieve the blocking synchronous wait operation done. So our background slash red should be able to pick up the operation, run it, and here just stop and wait for that thread to be done. Let's see if this works. This is as a note for blindly trust what LLMs tell you. Let's click. Oh, what happened? System invalid operation. Exception cross-thread operation not valid. Rich text box 1 access from thread other thread it was created on. Oh, okay. So we have effectively violated the prerequisite that elements be modified any other thread that the one they supposed to be modified from, the one they were created on. In case it's the white thread. So this didn't seem to help us. Let's think about it. Is there anything to bypass it? What could be? At this point, running out, so slightly basically have a sandwich just before dive into synchronous think afterward or the final update or so output. So what I did here extra primitive this set I call it variant by default set to that start right. Oh, then reset the barrier so it's gonna be false. Try to invoke synchronous keyword of and lastly all our after where we wait on. Notice the synchronous operation which is a task has to continue with something. It's something you're gonna see a lot or hear us talk about it quite often when it comes to sync patterns. So each task or a synchronous operation has a continuation. In this case, we explicitly tell the task what should happen once the task itself. So just one of two possible done states, which success or failure, but that's something about right now. And the continuous case would be an action taking our task and doing something with it, in this case we're ignoring it, and simply setting the barrier indicating that the task is done so we continue, which is what we want, or we want after method to first wait on the barrier, signaling that yeah, the deadlock token was written. Element can write a second one after deadlock. Would this work? Well, let's give it a try. Basically, I guess it wouldn't work, but I hope you. Or I press the deadlock button, but let's convince ourselves. Okay, so we are basically here in the after. That's good, and the call stack is essentially button click. So we are here because it says it's a task that we don't wait on, so we immediately dive into the after. And now we block at this point. See, we can see that we have 4 deadlock indicator, effectively nothing. Pause the execution because given it enough time and see what well, as you can see, I paused it. It's still in wait call barrier object after method. Otherwise, you can see synchronous logical stack. And here on it, we see same promise that was scheduled, but being scheduled got to execute. So we have basically the same. We're waiting, we're blocking the UI thread by waiting on the barrier, and because of this, the actual operation got that promise task actually. Well, that never gets to get executed. Little a say as the gotta break vicious circles. One desperate attempt of doing just that and exiting the circle would be to simply put the after call to the after method side the continuation body select expression here. So the idea would be the task is done at some point, and what will happen is that the deadlock should be written element. Then we continue by setting the barrier. It's fine. Then calling the after method that waits on the barrier. It should amount to doing nothing because the set, and then we can simply after that. And here you're gonna see another interesting side effect. Let's run the code. Looks happens. This time round, it's gonna work. Let's see what we get. Oops, we after method. This is nice. So we're waiting. Let's reduce the wait. Okay. So Y is responding at B. Right on here, but there's no after deadlock written. Why is that? Why is well? I don't know. Is this actually a deadlock that we're not noticing? Could it be? Press the button once more. I suppose not responsive, but well, here we are again in the after. So no deadlock, and again, as you can see, yeah, we don't have much. We stood before deadlock, nothing happened. Barrier, and we call the right text, we actually do get to call the right text method. Let's dive into it and let's do it. Try to modify this property. Oh, now we see something interesting. Um, as you can see, at some point, we get to throw an error that no catches, and this error will leaks. That's a shame because error with exception tell us something important. Valid operation exception, cross-thread operation, valid control rich text box access from thread other than it was created on. So we've seen this before. This is basically happening because the continuation, so essentially the lambda expression embedded the call to the after method, is not guaranteed to be executed on the same thread as the button one click event handler. That is the necessary UI thread. So that's not good. How can we fix this? By fix, I just mean patch it up, but the thing is gonna, well, bleed. It's not really gonna uh, guarantee that whatever we do is not going to cause other problems. It's like patching up, but not disinfecting it, so it actually fester. The thing we can do is to pay a little bit of attention what's going. So I'm gonna just to you. I have the solution right. I'm gonna do call the right text to sync method, the deadlock token that we want. Difference is that now I'm gonna set to this task and order it to capture the execute context and continue. That's what this method essentially does. Again, I'm gonna go into details, but if don't set it explicitly to true, the continuation is guaranteed to run on the same, uh, yeah, same threads as one you came from. After context, it could run on a different thread pool thread. It's exactly what caused the problem we had. And as you can see, I'm doing a little bit more than that. I'm actually taking the so-called waiter, and when I'm setting this event handler to delegate on completed an action that sets the barrier and otherwise the configure wait is not really returning a task, so I cannot simply say continue with. I need to do it this. Only way I can set a continue through this waiter on. Talking too much without seeing it in action doesn't help us to know what's happening. Let's do just that. We have reached this nasty point and write the text. Well, and delved in task waiter code. Rollback. See pretty quickly, but let's just run. Oh, see the after deadlock being written. Exactly what we wanted. Finally, to catch the exception context and ensure that the after uh, call is executed on continue. That runs on the same threads. Right now, at least have something that looks a little bit remotely to a functional solution. It's not a solution, it's a workaround and suboptimal workaround. So the question is, what can we do this thing better? Anything at all, but still inconvenient. So we simple tasks did. It's worth asking, what do we do about these tasks? The having the potential, we don't keep track of them consistently longer. What I mean by that, launch a task and don't actually wait for it to be done, otherwise we block. So that's exactly the problem we're trying to avoid. And we don't know when that task is actually done. Any kinds of signal, whatnot, signal the appearance of the actual end of the line for what operating task we're doing. But that's not really enough for us. So at least conclude this present session. Let's look at a more complicated design. What would happen, for example, if I were to click the deadlock button? Succession. Well, one problem would be that I'm launching a task. If I'm not careful, I could then launch a task, which would then compete with the same one for this resource. Well, that's not very problematic because, at least in this simple example, there's no serious base condition issue that could later on cause faulty behavior. Still have an incoherent behavior. That I mean, when you press the button, the expectation is to see the before, the deadlock indicator, and after size order. Now, if you don't have control over succession of operations, sub-operations, they pollute the console output that we see here, in a way that makes it inconsistent, coherent, have overlapping operations, something don't really have, assume in this case, don't want to compete with one another, perform parallel, give the user parallel. So how can I avoid that? Well, one way of doing it would be like we've done it here. It's my but very interesting having this succession of calls. Or write text async after call. That's it. This callback then be scheduled coherently. I might click the button. This actually gets scheduled sequentially. Sequential doesn't rule out synchronous. So how am I going to do that? Well, I will make use of worker and I'll check there is. Then I don't need to worry about the worker anymore about that task. I don't care about it. The garage click can do its job. So what I can actually do with it, uh, start task, in this case a task factory. I need to do this because goes to task run. Task factory allows me to observe or inherit the synchronized context. Wanna do want to observe that synchronization context because whatever we run, this task factory operation has to access the UI. So it has to do it from the same UI threads as one where we are when the button one click and is handled. So that's the syntax, or these are the details of the start new reload that I'm using. The first one, of course, being the callback that declared here. In this case, this will schedule, or just a queue for scheduling a task that will actually execute this callback. Okay, that's fine because this is what typically happens the first time we run the application. But what might happen if you actually click the button quickly? In that case, I just don't want to spawn another task. I want to do the following. I want to use the task that hasn't yet completed and make it continue after it's done, of course, with the same callback. And the trick is to make it continue on the same synchronization context. Now, you see here that I actually call the unwrap method. And this is the method that's applied to an instance of this type, task of a task. So we call this an outer task wrapping an inner task. The same thing that task run does. So it provides you with an outer task that wraps an internal one. And if you await the outer task, the result is actually a task that you can await again. It sounds complicated, and it probably is for a novice in these matters. But effectively, what we do with the unwrap, make sure get our hands on the inner task, because otherwise, won't be able to successfully sequentially schedule different callbacks. We still have the same problem that we're not really aware when the internal task of the wrapper or outer task is done. That's what we're achieving through the unwrap call. So let's see this in action. I increased the delay to 2 seconds to have a little bit of temporal room and thus to be able to click the deadlock button in quick succession. The first time around, you should see that the task is created because the previous instance was already in the completed state. And let's go. I'll click it once, and twice, thrice. Look what happens. The first time, we are in a completed state, then we start a task. We see that before deadlock, milestone being reached at this time. Then we have the deadlock, and soon afterwards, 2 seconds later, the after deadlock marker. Then, nicely, or almost after a blink of an eye, start again. Before deadlock, deadlock, after deadlock. Finally, we continue with the last operation. So in this case, we have neatly organized the sequential execution, and we've done so from a synchronous function, or a function that at least has synchronous semantics. We've been able to sneak our way past a function or a method that actually requires awaitable semantics, the synchronous semantics. This one. I will conclude this presentation, this first part, with this conclusion. Next time, we ought to visit other more advanced techniques of achieving basically similar things, but we will mostly rely on controlling the synchronization context. Of course, we might not always be able to control the synchronization context, and we are, as in this case, obliged to preserve it, because that's what the UI framework requires from us, that we modify any UI element, a UI thread, so we cannot tamper with the synchronization context. We're obliged, we're bound to preserve. But there might be situations which that's not possible, or that's actually possible. You can do away with a different context. You create your own, or can even use a temporary one that's empty, in which case it would mean we're free to run the task, the synchronous operation, as you normally would on any available thread from the thread pool. That's also possible, and we will see how that would work. Of course, I'll repeat, it might not work well when working with a UI application, but there are other situations in which that's completely allowed. And again, our major hurdle is, our main goal is to work around this nasty situation, a scenario in which we have to call an asynchronous function from a synchronous one without using the await keyword. With a more careful design, you can completely make sure that you leak no resources. Thus, make sure that your worker task is being disposed of, which I don't really recommend. That's not what you're supposed to be doing. But at least when shutting down your application, you should check that the worker task was completed. That's another thing that's, again, completely doable. I will probably show you how to do that very quickly before we end this video. So this is the last trick. Wanna make sure that your pending task or tasks are actually done before you shut down your application, at least for informs allegation. This is what you can do in this event handler. In the form closing one, you can actually check if your worker is done. Well, I've not written production ready code here, but you get the idea. It's your job to make sure that there are no race conditions or other issues. But in principle, if your worker has not completed, what you can do is just cancel the order for closing the form. That's what you do here with this cancel flag, setting it to true. Then you perform the same idea. Following the same idea, you perform a continuation on your worker. After everything that was scheduled is done, you simply re-invoke a close action, and then you should be all but fine. Oh, this is it in action then. And I'm gonna, yep, see the frame form close event, and soon this will disappear, and it has disappeared. And that's what you could do to wrap it up and decrease the chances of some leaking or interrupting your uh, flow mid operation. I guess I'll see you next time for a deeper dive into the work of Asynchrony.